Okay, now what we want to talk about is the mathematics of simple harmonic motion. So here is our setup, and this is the graph of the, right? This is the graph of the motion, right? It starts at the amplitude, goes negative amplitude, positive amplitude, negative amplitude, da da da. So this is the cosine, right? So this is the x in meters versus time in seconds. And as I just said a couple minutes ago, this equation, this curve is described by this equation. X as a function of time, in other words, x depends on time, equals a cosine 2 pi little t over big T, over the period. Okay? So that equation describes that curve. All right, well, come on. When we did kinematics way back when, we learned that in order to describe something, you need x, velocity, and acceleration, right? Okay, well, all we have now is x. So the question is, how do we get velocity? Well, there's really two ways. Let's do it, one way that we learned. So the velocity is delta x over delta t, right? Well, if you have an x versus t graph, which is what we have, what is this? You better know this. It's the slope. Right? It's a slope. Oh, that's great. So that means that I can obtain the velocity just by figuring out the slope. So, right up here, okay, so right up here, the slope is 0, and then the slope starts getting, negative, 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 and it's 0 again, then it starts getting positive, We could just figure out the slope at every location, right? So that's one way we could do it, Just measure the slope at every point here. All right, and we get it right. All right, so again, let's just kind of think about that. We start off at 0, and then it gets negative, 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 negative. It's all negative, right? And then it gets to 0, and then it gets positive, okay? So that's one way we could do it. Another way we could do it is just think about it, right? Just think about it. So here's our setup. All right, so let's say that's A, that's 0, and that's negative A, right? Okay, so remember, we always pull it to x equals A, and then we let go. So initially we have 0 velocity, which agrees with the slope, right? The slope right there is 0. Then we let go, and it's going to go negative direction, so the velocity is going to be negative. So it's going to go faster, 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 faster. Now here, at x equals 0, the spring is not stretched or compressed. So that's when it's going to go maximum speed. Then here it's going to start going slower, 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 and then it's going to stop. And then it's going to turn around faster, but now it's going this way, it's going positive direction. So faster, 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 maximum speed, but now it's being compressed, so it's slow, 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 and all right? Okay, so either way, you can figure it out. And if you do that, this is what you get, right? So we start out at 0, and here it's kind of really, this is a steep slope, well, whatever. Here it's, from here to here it's negative, right? So you can see here, right? So right here, this is where it's a big, big negative slope, right? So we start out at 0, and the slope starts, the magnitude of the slope gets bigger, 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 bigger. Then the maximum right there, then the magnitude of the slope starts getting smaller, smaller, smaller until it gets to 0. So you can see right here, right? The magnitude, right? Starts at 0, gets more and more and more and more negative, then 0, then bing, 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 bing. But still negative, right? But the slope has come up here, and then it just keeps going, right? Then you're at 1, and it's positive, right? So this is above 0, it's positive. So anyway, just do what I just said. Just take your ruler and figure out the slopes, and you get this. Or just do the other way. You pull here, you're at 0, you let go, it goes negative. right? Faster, 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 faster. Here it's maximum speed, right? Maximum speed. And then it starts slowing until you get to 0. Then it goes positive, and then it goes negative again. Okay? Anyway, convince yourself that this makes sense, right? So this is the velocity graph. Now, let's see. We had x equals a cosine, I'll just say 2 pi ft. How's that? All right? It doesn't matter. Put it, whatever. So, but it's a cosine, right? The x is a cosine. What's this thing? So this is cosine. What's this thing? So that's what I mean. You need to know your trig functions, your graphs. So, I mean, sine is like this. So what's this? It's negative sine, right? Just sine flipped over. So we have the velocity equals some maximum, which we don't know yet, times sine, okay? Times sine 2 pi ft. Okay, so we get the x, and we got the v. Now we've got to get to a. All right, how are we going to get to a? Well, you already know, right? We're going to get to a by doing the same thing. You know, just figure out the slope. Okay, sorry, I forgot to say something. So a, as you know, a is delta v over delta t. So if we have a v versus t graph, then this is the slope. So all you have to do is the same kind of thing. So just figure out all the slopes here, you know. Just do that again. Or you can think physically too, right? Like here, you let go. Then here, you know, it's a complete change in direction. So there's a big acceleration here, big acceleration here. Either way to do it, but you're going to get an A graph. Can you do that? Oops, sorry. There's the velocity. And it's a negative sign, right? Negative sign. Oh, I forgot my negative sign. Okay, so there's your A graph. So we start out negative slope, then positive slope, right? Start out negative. See, the acceleration is negative, then positive. Anyway, what's that? Well, that's cosine. So what's that? It's just negative cosine, right? Negative cosine. So A is negative A max times cosine 2 pi ft. Okay, so there you go. We got our A, our X, our V, and our A. That's awesome. That's all you need to know, right, for kinematics. So that's great. All right, wonderful. Now, some questions for you. Let's see if you remember your how to find the sign of acceleration. Okay, a block oscillates on a vertical spring. When the block is at the lowest point, what is the sign of the acceleration? So remember, okay, A equals delta V over delta T, right? And that's V final minus V initial over delta T. So what we learned a long time ago is that the direction of A equals the direction of V final minus V initial. Remember doing that with the vector subtraction? We did that a lot way back when. So what I want you to do is just use this and figure out the direction of A when it's right there. So pause your video and make sure you do it. This is a good review. All right, let's do it. So it's going like this, right? Okay, so I would say right before it gets to the bottom, the V initial is like this, and then it gets to the bottom, then it goes back. So V final is like that. Agree? So V initial, or V before, and then V after. So what we want is V final minus V initial. So V final minus V initial, okay, V final is like this. Okay, minus, remember how to do a minus? So minus is, okay, V final minus V initial is V final plus negative V initial. Remember that? You got to know that, all right? So we have that plus negative that, which is that, right? Which is right? So with this coordinate system, it's positive. So it's kind of important that, it's not kind of, it's super important that you know how to do that. So, or if you don't know how to do that, make sure you review and figure it out. Here's another one. A block oscillates on a horizontal spring when the block is here, right? So the block's going like this. Okay, so when a block gets to here, minus a, what's the sign of the acceleration? And we're just using the same regular thing that we always use. So to the right is positive, to the left is negative. So pause your video and figure it out. Okay, you're back. So right before it gets to minus a, it's going this way. So that's a V initial. And then it stops and it turns that way. So that's V final. So V final minus V initial is this plus a negative that, which is that, which is that. Right? So the acceleration at x equals minus a is positive. And I hope you can figure out what's going to be the sign of the acceleration here. So V initial would be this way, V final would be that way, so the acceleration here would be negative. Okay, so all right. So let's go to here, right? So we said acceleration at x equals minus a is positive. Here's our okay, so here's our graph. This is x graph. This is our x equals minus a, right? And here, guess what? So the acceleration is positive, yay, okay? So all I'm saying is it works, right? The graphs work. But you got to make sure you understand it, though. All right, now, we're not, I said we have x, v, and a. That was sort of a lie, or not telling the whole truth, nothing but the truth, right? So we have the graphs for x, v, and a, but, here I just wrote v max. Well, what's v max? I mean, it's the amplitude of this graph, but what is it? Here I wrote a max. Well, what is it? I mean, we have the amplitude here. It's just a. But, a is just x max, right? But we don't know what a max is. We don't know what v max is. So the first time I taught this class, I used like 10 slides, and I showed all the math, how to get the v max and the a max. And I thought to myself, man, that's a waste of time. So right now, I'm not going to do that. I'm just going to give you the answers, because I don't think it's really super crucial that you know how to calculate v max and a max. All right? If you want to know, just look in the book, and you can read pages of math. All right? Okay, so you look in the book, and it turns out that the maximum velocity is 2 pi amplitude frequency, and the maximum acceleration is 2 pi frequency squared times amplitude. Okay, I don't think that's super crucial to know. If you need it, you just look it up. But here's the important thing. So now, look, we know what x is. For any time, we know what x is. For any time, we know what the velocity is. For any time, we know what the acceleration is. Right? I'm assuming you know a, because you set up the situation, you know a, right, when you set it up. So basically, if we have something undergoing simple harmonic motion, we know x, we know x max, we know x min, we know v, v max, v min, a max, a min, and everything in between. So basically, as far as kinematics, we know everything. Everything. So we're done. Okay, we know everything as far as kinematics. As long as we can show that something undergoes simple harmonic motion, we know everything there is to know about the kinematics. Oh, so there it is. Here's just the same thing, right? I'm just the same information. So here's the x, the nice cosine. Here's the velocity, the minus sine. Here's the acceleration minus cosine, right? So there's the equations. And then here's the X max and the V max and the A max, right? Same information as the previous slide. Okay, woo, finally. All right. So a mass oscillates on a horizontal spring. The velocity is Vx, no kidding. And the spring exerts a restoring force Fx. At the time indicated by the arrow, figure out the signs of the velocity and the force. And careful now, this is the spring exerts the force on you, right? So that's the restoring force. So everybody please stop and pause your video and figure this out. Okay, so you notice that it's right here, right? Right there. That's the time, right? Now, this is after one period, but before the second period, all right? So what does that mean? Okay, so look, that's one period, agree? So one period. Now, hold it. So here's a half a period. That's this. Then there's a full period. Then there's 1.5 periods, and there's 2. So we're right between 1 period and 1.5 periods. Okay? So again, 1 period and then a half, right? So we're going in this direction. Agree? So we're squishing or compressing the spring. So the velocity is negative, all right? It's negative. So the spring is being compressed. So if the spring's being, what do you mean F being 0? Okay, well, I'm sorry, I blew it. So 1 period, yeah, that's right, sorry. This is 1.5 right here. So this is between 1.5. Sorry, so 1, and then we're right here, right? So we're going to the left, agree, it's going to the left, but we're at the equilibrium point. Oh boy, right? So what's the force at the equilibrium point? 0. All right, 0. Okay, make sure you understand that. Sorry for my goof up. But anyway, you should be able to figure, if you see a graph like this, you should be able to figure out, the sign of x and the sign of the force. All right, let's talk about energy. I mean, super important energy, right? So if we ignore friction and we have, ideal springs, energy is conserved, right? So let's think about it. So again, we pull the spring to x equals a, let it go. So right now we're holding that mass. So all it is potential energy, no kinetic. Okay, so we have the total energy, E is kinetic plus potential. So when we pull it here, we're holding it still. So we have all potential, no kinetic. So the total energy is just the potential energy. Then we let go, starts going faster, faster, faster. So the potential energy gets smaller, right? Kinetic energy gets bigger. And the total energy is always the same, right? Because there's no friction. The total energy is constant. So this plus this equals that. Okay, then we get to here, and the spring is not compressed or stretched. So the potential energy is 0. So it's all kinetic. It's going as fast as it can. So no potential, all kinetic. So the kinetic plus 0 is the total. Then we're going here. It's slowing down. So it's compressing the spring. So the potential energy is increasing, right, from 0 to that. It's slowing down, so the kinetic is getting smaller from here. And this plus that equals that. Then it gets to here. It stops. So it's fully compressed. So there's no kinetic, all potential, so the potential is the total. So there you go, right? And this is kind of a nice thing, right? Because it has the signs of the acceleration, right? And this acceleration is 0, maximum speed, no speed, and all that other stuff. So that's a nice graph. Here's another way to look at it. And we've discussed this before. So we know that the potential energy due to a spring is half kx squared, which is a parabola, right? And so this is where it turns around. Turning point, remember the turning point from a long time ago at x equals a? This is the other turning point at x equals minus a. The energy is purely potential, right? Here, there's no potential, it's all kinetic. And look, if this is the total energy, which is constant, if this is the potential, where's the kinetic? Well, it's right there. Remember, we did that before. So the potential energy plus the kinetic energy equals the total energy, right? The potential energy plus the kinetic equals the total. So all potential, no kinetic equals the total at the turning points. So that's another way. Okay, and now here, if you want to get really fancy, if you want to, so here's the potential energy. So what's the kinetic energy? 0 gets bigger, 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 maximum, then smaller, smaller, smaller. So if you want to, you can plot, here's the potential energy in the blue, here's the kinetic energy in the green. And this plus this is the constant E. That's another way to look at it. So you should be familiar and comfortable with all of those energy graphs. All right, now, okay. So the total energy equals kinetic plus potential. Kinetic plus potential, it's constant. Wonderful. Now, you know, typically when we have these conservation equations, we just say that it's constant. You know, we just leave it at that. It's constant. But here, you know, we can actually evaluate this constant. All right? We can actually get a number for it. All right? And so let's do it. Well, I want you to do it, actually. So remember, this is true anywhere for any value of x, which means for any value of v. This is always going to be true. So what I want to do is, again, figure out the constant. So what I want you to do, take any position of x, take any value of x you want, and at that value of x, figure out v. Okay, so if you know the value of x and you know the value of v, then you can figure out what the energy is, what the constant is, okay? So be lazy, you know? Pick a x where you know the v and do it in an easy way, and you'll figure it out. So pause your video and please figure it out. Don't just watch me doing it. All right, so hopefully you've figured it out. So what's the easiest one you can possibly imagine? Well, at x equals plus or minus a, right? What's the velocity? It's 0, yeah? So therefore, so if you say at x equals plus or minus a, we have E equals 1/2 mv squared, which is 0, plus 1/2 k plus or minus a squared, which is a squared. So that's the constant. Ta-da! Is that cool or what? All right, so that means that the energy is always constant and is equal to 1/2 k amplitude squared. Always. So that's kind of cool. Oops. All right. Okay, your turn. A pendulum is pulled to the side and released. The mass swings to the right as shown. The diagram shows positions for half a complete oscillation, right? So here, so that would be 1, right? This would be 1 complete period. But it's only showing half a period. Okay, so it's going whoosh. Okay, so at which point or points is the speed the highest? Where's the magnitude of the acceleration the greatest? And where's the magnitude of the restoring force the greatest? So if you've been paying attention, you should be able to figure that out. So pause your video and figure it out, please. All right, let's go. Okay. Here, it has all, okay, first of all, it's simple harmonic motion, so the energy is constant. And the energy is potential plus kinetic. Here it has all potential, it's not moving. Here, it's going to be 0 potential, right? All kinetic. And then here, it's all potential and 0 kinetic. So where is the speed the highest? Where is no potential energy? And where's that? Right here. So the speed is the highest at c. Okay, where's the magnitude of the acceleration greatest? Well, where is the magnitude of the acceleration greatest for the horizontal spring? At the endpoints, right? At the amplitudes. Because it was before, after, before, after. So the magnitude of the acceleration is going to be greatest here and here. Because, you know, V initial, V final. V initial, V final. All right? Just like with this horizontal spring. And then, so look at, if you have a greatest acceleration here, F equals ma, right? So the restoring force is going to be the same. Okay. All right. Okay, now we want to finish those two problems we started earlier with the dropping an object through the earth and the pendulum. Okay, so look. Oh, sorry. Before we do that, got something else. Okay. Let's see. The energy of the spring is 1/2 Ka squared. Right? Right. So please do this problem. So please find an expression for the maximum velocity. So just use this and find an expression for the maximum velocity. So pause your video and please do it. Okay, so where do you have the maximum velocity? Where the potential energy is 0. So you're going to have 1/2 mv max squared equals 1/2 Ka squared. So you want to solve for V max, so multiply both sides by 2, divide by the m, take the square root, V max equals a square roots of K over m. All right, so there you go, right? So V max is a radical K over m. Now, why do I want to know that? You'll see. All right, so we just figured out that V max is a square roots of K over m. Now, earlier, how much earlier? I don't know. Hold on. Oh boy, oh boy, oh boy. Oh, there. Okay, earlier, I didn't derive it, I just told you that V max is 2 pi Fa. So we also know that V max is 2 pi Fa. Wow, golly, what are we going to do? Well, we're going to put them equal, see what we come up with, all right? So let's put them equal, see what we come up with. So what we want to do is we want to solve for the period and the frequency. So we can figure out the frequency, you know, of that object going through the earth, and also the frequency of the pulley. I mean, the simple the pendulum, not the pulley, the pendulum. All right, so we have a square roots of K over m equals 2 pi Fa. Okay, so the a's divide each side by a, then divide both sides by 2 pi, and there's the frequency, right? There's the frequency. All right, and what's the period? The period is 1 over the frequency, so it's just 2 pi square roots of K over m. So here you have an equation, two equations, right? Here you have equations for the period and the frequency. And look at, these equations are true for any object that undergoes simple harmonic motion. Anything. Now, what's kind of cool about this is, look, it doesn't depend on the amplitude, right? It doesn't depend on the amplitude. So that means, let's say we had a grandfather's clock. That means that the period for this is going to be exactly the same as the period for that. Well, right? I mean, using the small angle approximation, okay? Or with a spring, it means that the period for the spring, right, is the same for this guy as it is for this guy. Now that doesn't seem obvious, does it? Or like the pendulum, right? The pendulum, you know, you let go. This has a big amplitude. This has a little amplitude. You know, the periods are the same. The frequencies are the same. That's not intuitively obvious in my opinion. Here's a tuning fork. So I'm not a musician, but I know some of you are. So this thing is supposed to produce a C, 512, okay, hertz or something like that. Now look, this thing is always supposed to produce the same note, the C, right? And so it's going to produce a C if I just have a small amplitude, woo, or a large one, all right? Small or large. It's the same frequency. So see, this is these things go back and forth, right? So the amplitude is irrelevant. The period and the frequency is exactly the same. Doesn't matter what the amplitude is. Okay, now look at these equations again. All right, so here's my period, here's the frequency, here's the period. So what do they depend on? I mean, you already know what the mass of the object is, right? I mean, you set up the thing, right? So what do these things, what does the frequency depend on, the period depend on, the restoring force depend on? What do they depend on? I hope you understand that they depend on K, right? K, you know? So in other words, for any problem with simple harmonic motion, if you know what K is, you know the frequency and you know the period without doing any work. Bingo. So that's kind of awesome, right? All right, so and look at it. I mean, it's not just that. You know, if you know the K, I mean, here's the F, right? But the F has a K, right? So if you know the K, you know everything there is to know about the kinematics, the frequency, and the period. So basically, if you can show something undergoes simple harmonic motion, and you can figure out the K, you've solved the problem. You know everything there is to know. Okay, let's quit. How long was that?